welcome to this video on amount of substance. This is a revision video for AQA, specifically for the AQA exam board, and we're basically just going to go through an overview of all of the amount of substance aspects that you need to know for the exam in particular. I should say that the PowerPoints that I'm using here, these can be purchased. If you want them for revision, they're really good for that. You can print them out, you can go through them in your own time, etc. If you look at the link in the description box for this video, you click on that link and that'll take you to the place where you can get them from. Okay, so let's just remind you that all these videos, they are tailored to the specification. Obviously, these are the specification points for AQA, and they're basically designed to cover the content as an overview. Okay, so let's start with the mole. This is something called Avogadro's number we're going to be looking at. Okay, so the mole is obviously very important in chemistry. It's used a lot, and we need to know that basically it's just a way of measuring the amount of substance in chemistry, and sometimes it's shortened to the letters mole. And basically, 1 mole of any substance contains 6.02 times by 10 to the 23 atoms or molecules. This number is known as Avogadro's number. So, for example, we had 1 mole of water. That would contain 6.02 times 10 to the 23 molecules of water. And 1 mole of iron would contain 6.02 times 10 to the 23 atoms of iron. So basically, I think you get the idea that 1 mole of any substance, whether it's an atom or molecule, will contain that many of the atom or molecule. Okay, so we can actually calculate the number of particles, and sometimes they can get you to do this in a substance. It's dead easy. All we do is you just take Avogadro's number and multiply it by the number of moles. So if you had 1 mole of substance, it's literally just Avogadro's number. So it's pretty straightforward. So here's an example. So if we're looking at how many particles make up 0.67 moles of ammonia, this could be a question they could ask. All we do is we use the formula, number of particles is Avogadro's number times the number of moles. So that's 6.02 times 10 to the 23. Multiply that by the number of moles, 0.67, and we should get that many particles. Now it's a lot, but obviously particles are very small, so you would have a lot of them. Just be prepared to rearrange this formula as well. They could obviously ask you to work out the number of moles of something, and they'll give you the number of particles that are in there. So just be kind of aware that they might get you to do that. Okay, so let's look at the mass and MR, or mass and Mr. Okay, so this is where we're looking at the number of moles using the mass of something. Normally this is for solids, pretty straightforward really for this. So the number of moles is just the mass over in grams over the MR or AR. So if you're using a molecular formula or molecule or compound, you'd use the MR, or if you're using just an atom, or an element, you would use the AR for that element. So here's an example. So if we calculate the number of moles, or once we calculate the moles of 23 grams of gold, we're going to give our answer to 2 significant figures. So the number of moles is mass over atomic mass, which is AR. So the number of moles is 23 grams, because that's what we're using, divided by 197. That is the AR of gold. And basically we'd have a number of moles of 0.12 moles. And this is, remember, to 2 significant figures. Really look out for the accuracy there. Again, be prepared to rearrange it. These will be integrated within questions, so you've got to know how to rearrange this as well. Basically, a way in which you can kind of know if you're going to use this, look in your question. If you have any 2 of these in your question, whether it's moles, mass, or AR, you obviously have to work that out from the periodic table, then you can use this equation. You might have worked one of these components out already previously in your question, so make sure you look back in your questions and make sure that you see if you've got that information. I've got this saying really, if in doubt, work out the moles, because from the moles you can work out a lot of other things, and you'll probably hear me say that again later on in the video as well. Okay, so that's okay if it's for a mass of something like a solid, but what about solutions? Solutions obviously are slightly different. So the number of moles in a substance in a solution can be calculated from its concentration and volume. So here's the formula that you need to know. So the number of moles is concentration in moles per dm cubed times by volume. Now, the really important thing is volume must be in decimeters cubed. So quite often they give you it in centimeters cubed, and you've got to convert that. All you do is you just divide by 1,000 to get that into decimeters cubed. So that's pretty important. You can also just add times 10 to the minus 3 onto the end of your centimeter cubed volume. And that basically does the same thing. It's just a little bit neater, a bit quicker. If you're all right with maths, you should be comfortable with that. So here's an example. Calculate the number of moles of 200 centimeters cubed of 0.35 moles per dm cubed HCl. So the number of moles is concentration times volume. Now notice the volume they've given us is in centimeters cubed. There it is, look. So we've got to convert that. So the number of moles is 0.35, which is the concentration, times by the volume. And notice, you see, I've put the times 10 to the minus 3 on there. That means the same thing as divide by 1,000. And we do that to convert that volume into decimeters cubed. And obviously, you put that in your calculator, you get the number of moles to be 0.07 moles of this substance. Okay. Right. So, there you go. That just emphasizes your times by 10 to the minus 3. Again, just like the previous one, be prepared to rearrange the formula. You've got to be able to do that. And again, look in the question. If you've got any of the two components that's mentioned in here, you can use this formula. So look out for moles, look out for concentration, look out for volume. Again, I'm going to say this again, if in doubt, work out the moles. Because if you know the moles and you know one of the other ones here, you can work out a concentration or a volume. So again, the moles, just like with the other equation, you can work out a lot of things if you know the moles. Okay, gases. Right, gases are a bit strange because they occupy different volumes depending on the temperature. So we have to take this into account. And pressures obviously has an effect as well. And to get around this, we use something called the ideal gas equation. So the number of moles in a specific volume of gas is basically what we're going to use for the ideal gas. Now, the equation is this thing. It looks a bit weird. You've got 5 different factors here. So it's PV equals nRT. Now, really important thing, you need to know what these mean. So P is pressure. And it's got to be measured in pascals. If they give you it in kilopascals or micropascals or whatever, I doubt it would be micropascals, but if they give you it in kilopascals, convert to pascals. These are standard units. Volume, this is the tricky one. Volume's in meters cubed. Very often they'll give you the volume in centimeters cubed. Make sure you can convert. I'll go through conversion of units later on, but it must be in meters cubed. N is just the number of moles. That's in mole. That's pretty easy. The gas constant, which is R, that's given 8.31 joules per Kelvin per mole. You'll be given this in the exam, so don't worry about remembering that. And temperature is in Kelvin. That's important. If they give you in degrees Celsius, you must convert to Kelvin. It's basically 273 plus whatever the degrees Celsius is. We'll get that into Kelvin for you. Okay, so let's look at an example. So calculate the volume in centimeters cubed of 0.36 moles of a gas at 100 kilopascals and 298 Kelvin. So, first thing, write out your equation. You get a mark for this and rearrange it. So PV equals nRT, and you rearrange this to give V equals nRT over P. Make sure you're familiar with rearranging. So volume is 0.36. This is the number of moles that we've been given. Times by 8.31, that's the constant. You'll be given that. 298 Kelvin, this is obviously room temperature. Divide that by, now the pressure, look at the pressure. They've given us 100 kilopascals. Our pressure must be in pascals. That's why we've got 100,000. Got to be in pascals. Put all that in the calculator and we should get a value of 8.91 times 10 to the minus 3 meters cubed. Okay, that's the standard units. That's what we've got to use. There it is. The answer, the question said we need to convert it into centimeters cubed. Now, to convert from meters cubed to centimeters cubed, we have to multiply by 1,000,000. Again, I'll show you the a little bit later on why we multiply by 1,000,000. But there's our volume in meters cubed, multiplied by 1,000,000, and we get it in centimeters cubed, 8910 centimeters cubed. Okay, so yes, so let's look at we'll look at the converting units just on the next slide. But the important things, ideal gas, make sure you use the units above, they're the standard units. Make sure you can rearrange it as well, that's really important. The gas constant will be given to you. Standard conditions are 298 Kelvin and 100 kilopascals, that's pretty important. Okay, let's convert these units because obviously this is pivotal to all this. Okay, so I'm going to break it up basically into meters, decimeters, and centimeters. Basically, a meter is the base unit that we're going to use. Decimeter is basically a tenth of a meter. So this is 10 centimeters effectively. So like decade, deci. Centimeter is like century is 100. So it's 100th of a meter. So you might have obviously seen these before. Obviously meters, decimeters, centimeters. Now the little squared bit on the top tells you the dimensions that we've got. So for an area you would use meters squared, decimeters squared, centimeters squared, and volumes are 3 dimensions. So it's 3. So we've got the little 3 there. So we've got 3 different dimensions, and we have to take into account all of them. So let's look at the first one. So to go from meters to decimeters, we multiply by 100. And to go from decimeters to centimeters, we multiply by 100 as well. So because we've got 10 decimeters in a meter, 10 centimeters in a decimeter, and 100 centimeters in a meter. So if we want to go, the full hog, going from meters to centimeters, we do 10 times by 10, and that effectively means we're times it by 100. So that's how we get there. Obviously going backwards, it's just the opposite. Okay, so the general rule is basically for every dimension we add a 0 from the previous dimension. So if you look at this one, this is 1 dimension. So if we're going to go from meters squared to decimeters squared, we need to multiply by 100. We add an extra 0 onto there, okay, from the previous dimension. So meters squared to decimeters squared times by 100 times by 100 for this one. We've just added there. And obviously going the full hog, we just times 100 by 100 and we get 10,000. So to go from meters squared to centimeters squared, we multiply by 10,000. And obviously in chemistry we're looking at volumes. So again, we add a 0 for the extra dimension. So it's times by 1,000 to go from meters cubed to decimeters cubed. Decimeters cubed to centimeters cubed, we multiply by 1,000 as well. And obviously to go the whole hog, we from meters cubed to centimeters cubed, like in the previous example, we do 1,000 times 1,000, which will mean times by 1,000,000. Obviously going back the other way, you just divide by the same numbers that's shown here. So really important, you need to know how to convert your units. Okay, so there we go, that just confirms it. Right, so ionic equations. Now these are pretty important. Basically these show the ions which are formed in solution, and they show which particles are reacting. Now you've got to be able to do these pretty straightforward, but normally the things which are in solution, the ions in solution, are acids, bases and salts. So we'll look at this equation here. This is a standard balanced equation. This is for an acid reacting with a base. So this is acid, there it is there, sulfuric acid plus base gives salt plus water. Now what we're going to do is we're going to write the full ionic equation for this reaction. Now all we do is we take the bits which are basically ionic in solution, and we split them into the ions. So what we mean is the positive ions and the negative ions. Sulfate is negative, H is positive. So we split them up and we get this. Potassium hydroxide is aqueous. Again, we split them up. We've got 2 K pluses and 2 OH minuses. Potassium sulfate, again, there's your acid, there's your base. These can form ions in solution. And your sulfate is a salt. That forms ions in solution. So you get 2 K plus and 2 SO4, 2 minus. The water is neither an acid, base or a salt. So we just leave that as it is and we form H2O. Now, we need to form an ionic equation. We're looking for ones where the important ions effectively. So what we need to do is cancel any ions that appear on both sides of the equation to form the simplest ionic equation. So let's cancel them out. There you go. So you see the sulfate and the potassium, they appear on both sides, so we cancel them out. And we rewrite the equation to form whatever is left. So 2H plus 2OH minus will form 2H2O. That is effectively a neutralization reaction. So these sulfates and potassiums are called spectator ions. They don't actually get involved with the reaction. Okay, so this is the full ionic equation, and the charges must balance on the left and the right, and they should do it already if you've done it correctly. So there's an ionic equation, pretty simple actually when you look at it. Right, so we're going to use these equations to work out masses. Okay, now you need to know your state symbols. State symbols are S for solid, L for liquid, G for gas, pretty straightforward. And AQ is aqueous. Basically, this just means anything that's dissolved in water is aqueous. Acids, for example, are aqueous. Okay, so balanced equations, we can use these to work out theoretical masses. This is ideal when you're using it to work out the percentage yield of something. You need to work out the theoretical mass that's produced to be able to work out percentage yield. So this is where it could fit in. Okay, so let's look at this one. Calculating the theoretical mass from an equation. So how much calcium oxide, CaO, can be made when 34 grams of calcium is burnt completely in oxygen? Okay, so the first thing we need to do is write out our equation. You can see 2 lots of calcium plus oxygen will form 2 lots of calcium oxide. Make sure it's balanced as well. The next thing we have to do is basically work out the MR or the AR of the species involved. I'm going to write these masses in grams. So you can see here the MR is 40 for calcium. Because we've got 2 of them, it's going to be 80 grams. And the 2 lots of calcium oxide is obviously 56. Times it by 2 because we've got 2 of them is 112. So basically what we're saying is 80 grams equals 112 grams. Okay. Then what we have to do is divide the calcium side by 80 to find 1 gram, then multiply by 34 to get 34 grams. So because we want to work out, we don't want to know what 80 grams of calcium would produce. We want to know what 34 grams is. So we divide by 1 to find 1 gram, multiply to find the 34. So here we go. There's divide by 80 to get 1 gram, multiply to find out what 34 grams is. But the great thing about this method is the little units here, your divides and multiplies, we do exactly the same on this side. So we divide that, so 1 gram of calcium will form 1.4 grams of calcium oxide, but 34 grams of calcium will form 47.6 grams. So you see we're using the same division and multipliers on this side as we are on this side. So this is our leading side, and this basically we're using this to work out what we divide and multiply by, and we get the same on this side. So it's pretty straightforward. So this is the theoretical mass that we've worked out. And in theory, if we use 34 grams of calcium, we should, in theory, in a very perfect world, we should get 47.6 grams of calcium oxide. We can't get any more. That is the maximum we can potentially get. Obviously, we lose products when we do reactions, etc. So the amount you get in a practical might be lower. Okay, using equations to work out volumes of gases. Okay, so we can use balanced equations to work out the volume of a gas. So here's an example. What volume of hydrogen, H2, is produced when 12 grams of potassium reacts with water at 100 kilopascals of pressure and 298 Kelvin? The gas constant is 8.31. Okay, so the first thing we need to do is write out our equation, just like the previous step. So write it out, make sure it's balanced. Okay, then what we have to do is then have to work out the number of moles of potassium. So the number of moles of potassium, again, like I said, if in doubt, work out the moles. So we can work out the moles because we've got a mass and we know the AR of potassium because we can work that out from the periodic table. So by doing that, we've got 12 grams divided by 39 gets you 0.31 moles of potassium. Remember, we're wanting to work out the volume of H2. So if I know the moles of potassium, I can work out the number of moles of hydrogen. It's a 2-to-1 ratio. So 2 moles of potassium react to produce 1 mole of hydrogen. The moles of hydrogen in this case is 0.31 because that was the moles of potassium, divided by 2, and that gets us 0.155 moles of hydrogen. We've worked out the moles of hydrogen because from that we can now work out a volume. So use your PV equals nRT because we're dealing with gases here. Rearrange it to get V equals nRT over P. So volume is number of moles, which we've just worked out, times by the ideal gas constant, times by the temperature, we were told the temperature is 298, divided by the pressure is 100 kilopascals. Remember to convert to pascals, 100,000. So the volume is 3.84 times by 10 to the minus 3 meters cubed. Okay, so it's pretty much as simple as that. Again, we've used the moles, look. Once you know the moles of one of these substances, you can work out the moles for any one of them. Just make sure you use your molar ratio. Okay, titrations, absolutely crucial in chemistry. So these can be used to work out the concentration of an acid or an alkali. So you could, for example, have an acid or an alkali, either or, in a burette with a known concentration. So we know the concentration of it. But in your conical flask, we have an unknown concentration, but we have a known volume of a substance in there. And again, it could be an acid or alkali. It doesn't really matter which way around it is. We're going to add an indicator in there so we can detect the end point of our titration. So we add the chemical into the burette, into the conical flask, until the indicator changes colour. This is known as the endpoint. And we've got to add it drop by drop near the endpoint. We don't want to miss the endpoint. It's very, very subtle. Only one drop can make a massive difference. And at the burette point, if you look on this bit here, there's the burette. We've got to read on the meniscus. Okay, so the meniscus is this bubble that we see on the water, on the liquid that we're reading. We always read at the bottom, and you always read at eye level. So you can see this one is reading, that's 21, so this one's reading at 20. It's not reading at 19.8, which is this line. We're reading at the bottom of the meniscus. Very, very important that you do that. Okay, there it is. Okay, so, and then all we have to do is you record your results to 2 decimal places. And basically you keep repeating to get 2 concordant results. That basically means they are within 0.1 centimetre cubed of each other. As soon as you've got 2 concordant results, that's it. You take the average, and that is your average titer. Okay, indicators you could use. You can use phenolphthalein. In acid, it's colourless and it turns pink in an alkali. Or you could use methyl orange. It's yellow in acid and red in alkali. Now, obviously, titrations, you've got to be able to calculate these things. So here's an example of a calculation. So basically, titrations can be used to work out the concentration of an acid or an alkali. So here's an example. We've got 18.3 centimetres cubed of 0.25 moles per dm cubed of HCl. This is required to neutralise 25 centimetres cubed of potassium hydroxide. What we're going to do is calculate the concentration of potassium hydroxide. So, let's have a look. Here's an example. HCl is in our burette this time, and our potassium hydroxide is in our conical flask. The reaction that's going to happen when we add the HCl to the potassium hydroxide is this reaction here. It's already balanced, so we don't need to add any numbers to it. Then, again, just like the first step, we calculate the number of moles. We can work out the number of moles this time of our HCl because we have a volume and we have a concentration. So we can use these 2 numbers to work out the moles. So that's what we're going to do. Concentration times volume. 0.25 is the concentration. Volume's 18.3. This is in centimetres cubed. Remember, we need to convert to decimeters cubed. Times by 10 to the minus 3. That means divide by 1,000 effectively. Turns it into decimeters cubed. That should give us a volume, of 4.58 times 10 to the minus 3. Again, you can work it out and try it. Okay, so then we look at our equation, 1-to-1 ratio between HCl and potassium hydroxide. So the number of moles of potassium hydroxide is the same as the number of moles of HCl. So that is 4.58 times 10 to the minus 3. Again, very useful for, effectively, we need to work out the concentration of potassium hydroxide. So if we know the moles of it, then we can use that. Okay, and this is how we work it out. So concentration, using that equation shown you before, rearranged. Concentration is moles divided by volume. We know the moles, just worked it out. Volume, we've been told, is 25 centimetres cubed. 4.58 times 10 to the minus 3 divided by 25, again, times by 10 to the minus 3. That will give you a concentration of 0.18 moles per dm cubed. So that's basically how we work out the concentration. Here's another example. So we can work out the volume of something as well. So here's the one, 15.7 centimetres cubed of 0.45 moles per dm cubed of H2SO4 was required to neutralise 0.120 moles per dm cubed of sodium hydroxide. Calculate the volume of sodium hydroxide being neutralised in centimetres cubed. So again, here's the same thing. Different acids, obviously. Write the equation out. Again, balance it. Same thing. Then we need to work out the moles. The moles of the stuff that we've got. Sulfuric acid this time. We've got a volume, we've got a concentration. So this is going to be concentration 0.45 times by the volume. Again, look at the times by 10 to the minus 3 bit. Means divided by 1,000 because we've got to convert to decimeters cubed. Gives us the number of moles, 7.07 times 10 to the minus 3. Then we use the ratio to work out the number of moles of sodium hydroxide. This time it's a 1-to-2 ratio. So we're basically saying the moles of sodium hydroxide is 2 times by the number of moles of sulfuric acid because it's a 1-to-2 ratio. So the number of moles of sodium hydroxide is 2 times by 7.07 times 10 to the minus 3. And that will give 0.0141 moles. And then we need to work out the volume. So the volume is basically the number of moles divided by the concentration. So the volume is basically 0.0141. That was the number of moles that we've worked out before. divided by the concentration, which we already have. There it is. There's the concentration, 0.120. Stick it in, and we get 0.118 decimeters cubed. Now, we need to convert this into centimeters cubed. Remember from the conversions, 0.118 times by 1,000, we'll get it in centimeters cubed. So that's 118 centimeters cubed. Right, empirical formula. This is the simplest whole number ratio of elements in a compound. So here's an example. A compound contains 23.3% of magnesium, 30.7% sulfur, and 46% oxygen. What is the empirical formula of this compound? Right, first thing, write your elements. We've got magnesium, we've got an oxygen, we've got a sulfur. Then we need to write the percentages that we've been given as masses. So 23.3 grams of magnesium, 30.7 grams of sulfur, 46 grams of oxygen. Once we've done that, we need to divide these by the relative atomic mass to get the number of moles. So relative atomic mass of magnesium is 24.3, sulfur is 32.1, oxygen 16. Divide them and we get the number of moles for each. There we go. Okay. Then we need to divide by the smallest number of moles. Now here the smallest number of moles is 0.96. So divide all of them by 0.96. That is going to give us our whole number ratio. If it doesn't give you a whole number ratio, round it to get the whole number ratio if it's very close to a whole number. If not, if that was 2.5, you would have to double all of them to get your whole number. In this case, it's 1 to 1 to 3. So we've got 1 magnesium, 1 sulfur, 1 oxygen. There's your empirical formula. Don't worry if that looks a bit odd, because with empirical formula, it doesn't have to be obviously the same as the molecular formula. It's the simplest whole number ratio. But to work out the molecular formula, all we do is we just work out the MR of this. This is our empirical formula. Divide it by the MR of the molecular formula that they will give you, and we use this to multiply all the atoms in the empirical formula. So we can use that to work out that. Okay, so let's look at another one. So this is basically where we're using a hydrocarbon and it's combust completely to make 0.845 grams of carbon dioxide, 0.173 grams of water. What is the empirical formula of the hydrocarbon? This is very common in terms of burning of fuel. So all you're given now is a mass of the products of combustion. So again, what we're going to do this time, instead of writing the elements at the top, we're going to put carbon dioxide and water at the top. Now, if we write down the masses of these, just like we did last time, we've got 0.845 and 0.173 grams. Again, divide each of these by the relative molecular mass. This will get us the number of moles. Relative molecular mass of carbon dioxide is 44, and of water it's 18. So we're going to get 0.019 and 0.0096 of water. Okay, now, this is where it gets a little bit different. 1 mole of carbon dioxide has 1 mole of carbon atoms. So the original hydrocarbon must have 0.019 moles of carbon atoms. Okay, so that's really important. And if we look on, the main reason is because the carbon in the carbon dioxide and the hydrogen in water, they only come from the hydrocarbon. So if we look at the hydrogen side this time, so we've got 1 mole, obviously this tells us the number of carbons in the hydrocarbon. The water will tell us the number of hydrogens in there. 1 mole of H2O has 2 moles of hydrogen because it's H2O. So the original hydrocarbon must have 0.096 times by 2 number of moles of hydrogen. So it has 0.0192 moles of hydrogen atoms. It's really important. Okay, the carbon and the hydrogen from here have only come from the hydrocarbon. So that's what we're using here. Then now we've got the number of moles. We basically just do the same setup as we did last time. Number of moles of carbon divided by the smallest number. So we've got a 1 to 1 ratio in this case. So dead straightforward. Empirical formula in this case is just CH. Make sure you understand this little bit here. Okay, and you can use it. Okay, percentage yield. This is what I was talking about before. Percentage yield is actual yield over theoretical yield times by 100. So the theoretical yield is the amount of a product produced, assuming no reactants and no products actually are lost, and all reactants react fully. So we've got a complete reaction. So that was the method that I shown you before when you worked out the theoretical yield. So let's use this one. So in a reaction involving the complete combustion of calcium, 32.6 grams of calcium oxide was produced. The theoretical mass is 47.6 grams. Now, you would have to work out the theoretical mass, but save time, I've included it here. Now, the percentage yield is dead easy. Okay, so like I said, you've got to calculate that bit yourself. Percentage yield is actual yield over theoretical, 32.6 over 47.6 times by 100. In this case, the percentage yield is 68.5%. Okay, remember, yield is never 100%. You always, when you do these reactions, you always lose some reactants or some of your products, maybe lost. If it's a gas, for example, it might escape. Not all of your reactants might have reacted. So, or if you transferred it from beaker to beaker, you might have lost some. So yield's it's never, in fact, 100%. So, but we need to know what we're going to produce theoretically. Okay, atom economy. How efficient a reaction is. Atom economy is the molecular mass of the desired product divided by the sum of the molecular masses of all reactants times by 100. Different to yield, so you've got to watch out for that. Here's an example. So iron oxide, Fe2O3, can be reduced using carbon to make pure iron and carbon dioxide. Calculate the atom economy for the extraction of iron. So here's our reaction, look. Fe2O3 plus half carbon to Fe 1.5 CO2, so it's just balanced. So the atomic mass of the desired product, we're making iron, is 2 lots of 55.8. So remember, we've got to multiply it by 2. The mass of the desired product is 111.6, the atomic mass. Okay, so the sum of the molecular masses of all reactants, this is these here, so we've got to add them all up. So we've got 2 lots of 55.8, that's 2 lots of iron. 3 lots of 16, that's the oxygen bit, plus 1.5 times by 12, because we've got 1.5 carbons. We add all that up and we get 177.6. So we've got the mass, molecular mass of the desired product, and some of the molecular masses of all reactants. Stick that into your equation and we should get 62.8% as an atom economy. Different, because we're not using masses, actual masses, we're using molecular masses, and we're only looking at the desired product. And finally, importance of atom economy. Why do we need it? Well, to chemists, it basically tells us obviously how efficient a reaction is, as we know. But companies will try and use reactions that tend towards 100% atom economy. Basically, this means that the raw materials are used efficiently. It's more sustainable. We're using all of the raw materials to make our product. This means that we get less waste. We're not binning as much byproducts. And if we do produce a byproduct, companies try and make use of it. They try and make something with it. Higher atom economy means less byproducts, less time, less money spent separating them. So that's quite useful. So you just want your desirable product. And that is it. That is the amount of substance. Again, this PowerPoint, you can purchase it. If you just click on the link in the description box, you can purchase it from there. But that's it. Bye-bye.